All right, so on page 19, it tells you all the pressure units that are equivalent to 1 atmosphere. How many millimeters of mercury is 1 atmosphere?
760.
760. So that's related to the barometer questions you were looking at yesterday. If we had a pan of mercury here, pushing mercury up a tube, there's enough force and pressure in the room to push that mercury up 76 centimeters or 760 millimeters. And how many psi is atmospheric pressure? Yeah, it's only 14.7. So same pressure, it's just different units. Cancel? Cancel. So now we have 32 psi in a car tire divided by 14. That's what? About 30 divided by 15? Which is 2. What's 2 times 760? Well, 2 times 700 would be 1400. 2 times 800 would be 1600. What's a good number between 1400 and 1600? 1500? I'm guessing 1500. Chuck it in the calculator, see what you get. It's always a good idea to estimate. We'll go with 2 sig figs because 32 has 2. Lily, what'd you get?
16 and 1,654.
Okay, so this 6 would do what based on the next number being a 5?
Round up.
Round up 1700?
Yeah.
And that'd be mmHg. I guess it's a lowercase g. Yeah, that's pretty close to 1600, kind of like what we were saying. It's not exactly 30 divided by 15, so yeah, that's ballpark. I would trust it. Is 32 a smaller number than 110? Without units it is, but with units, 32 psi is 1700 millimeters of mercury. We're talking about, divided by 10, we're talking about 170 centimeters. We're talking about 1.7 1.7 meters. That's a lot of pressure in a car tire. So does it make sense that a car tire, bicycle tire can explode? Sure. Do you have to be walking around thinking that our arteries are ticking time bombs? No. Again, they only have 120 millimeters of mercury pressure. Now, does that mean they couldn't explode? I mean, that's basically what an aneurysm is. If you got like a weak spot in your artery, sometimes that happens in your brain. Hopefully they can go in, do brain surgery, kind of fix that so that you're not leaking blood and things like that. But yeah, we do not have to worry that our blood pressure is as high as a car tire. If it was, you would probably not be alive. Questions on that? All right, so if you take a look at page 23, we probably need 5 more practice problems related to that. So what I'm going to do right now is give you a minute to start out number 1 here. And when you convert 1400 mmHg, well, that's pretty close to what that one was, to atmospheres, you should get 1.8. If not, I can help you out. So you're going to do 1 through 5 for classwork homework, but you're not going to have time to do all 5 in class because we got to go over your homework and do Boyle's Law. But I'll give you time to do 1, check it, get some extra help if you need it, and then we'll move on. So see if you can't get 1.8 in your small groups. All right, any questions? Oh, the concert, and then the thing in the park is tomorrow.
Tomorrow, yeah. Oh, yeah, wait. Here, I'll tell you right now the times we put in.
Oh, yes. Can you actually just email it to me?
Yes.
Wow.
Yeah,
Because if you tell me, I'm going to forget. All right, anybody already get 1.8 atmospheres? Almost 2 atmospheres. Okay, keep going. Feel free while I'm waiting for other people to catch up. Try to knock out number 2, number 3. Just be careful with number 2. This is in pascals. Is there a number up here for pascals? No, there's a number for kilopascals, so you'll just have to incorporate the kilo prefix into your problem. Kilo is what power of 10? 10 to the third. Yeah, so you'll just have to include that 10 to the third in your problem. Would you agree if you put 1400 mmHg on top, you got to put mmHg on the bottom of your conversion? How many mmHgs are in an atmosphere? 760. So you're basically dividing by 760. What's 1400 divided by 760? Well, that's basically 14 divided by 7 or 14 divided by 8. So let's try both. 14 divided by 7 is 2. 14 divided by 8. Oh, we could reduce that. That would be what? 7/4? So that's like basically 1.75. I think the answer is between 1.75 and 2. I'm going to go with 1.8. 1.9. Sure enough, if you do the calculator, you'll get 1.8. Any questions on that? All right, I'd love to be able to give you more time on that, but we got to move on to go over your homework and Boyle's Law just to keep things moving. So if there's time at the end, I'll give you more time, however much time is left to knock those in. Any questions on that? Anybody not get 1.8? Anybody need some help seeing that? Okay, so let's go over your barometer, manometer homework from yesterday. Group 1, can you read your answer to question number 1? Just read the whole statement.
On high pressure days, the air pushes harder, causing the Hg to rise up.
Right. The air pushes harder, causing the mercury to rise up. Sing a little Hamilton there. And the pressure goes up the tube, and now we have mercury rising in the tube. Questions on that? All right, group 2, can you read question 2?
On low pressure days, the air pushes less, causing the mercury to fall down the tube.
Right. So if you're only pushing on that pan a little bit, you're only going to be able to keep the mercury up a little bit, and the mercury is going to fall. Questions on that? It's a pretty simple concept. Group 3, what is the pressure in this room?
1 atmosphere.
That's typically what pressure is, but we have an instrument reading it, right? 750 mmHg. So I have a feeling that when that was reading 750, there was probably a thunderstorm in the room. Like, we just got, what, 754 when we did it? Or maybe this was up on a mountain. Obviously, if you're up on a mountain, the air is thin. You don't have as many molecules pushing against the mercury. So I think the last time I checked Lidditz, kind of right at the top of the hill as you're coming into town, there's that new big brick building there. There's the big welcome sign to Lidditz. When I checked Google, I think that's about 381 feet above sea level. So obviously we won't be exactly at 760. That's really only true at sea level. So we might normally be at 759, maybe 758. But if it drops down to 750, 754, that's probably a storm system moving in. Any questions on how to read a barometer? Group 4, can you walk me through how to read a manometer? What's the difference in pressure?
I got 1726 mmHg.
Yeah, I'd say that's more so the answer to number 6. Let's work backwards a little bit. What's the difference in this YouTube? This manometer doesn't actually tell you the pressure of the gas. It tells you the difference in pressure. So what's the difference in pressure on that picture?
Is it 20?
Right, so this gas is pushing on this side, the atmosphere pushes on this side, there's a 22 millimeter of mercury difference. So, group 5, is the trapped gas pushing more or pushing less than this guy?
Less.
It's pushing less. So, you can see this side is pushing this much, this side is definitely pushing more, causing the mercury to shoot up on the other side. I always like to draw that in my picture, less pressure. So I know I'm going to have to get an answer that's less than 748. So if you don't get an answer that's less than 748, you know you accidentally went the wrong way. Josh, what did you have to do to get 726?
I took 748 minus 22.
Yep, so you subtract the 22. Sure enough, you get 726 mmHg. Good. Questions on that? Group 6. Which gas is pushing the most, the highest pressure? Letter A. Lots of pressure pushing down here. Normal pressure pushing down here. Good. Group 7. Which is the least pressure?
C.
Letter C. You have a little bit of a push here. You have lots of pushing over here. So therefore C is less. Back to group 1. What's the pressure in gas B?
Is it just equals out to 1?
Or whatever the barometer says. Yeah, so I would say C barometer. So this is an important point. Can you read the pressure of the trapped gas in that flask without a barometer? No, you have to use a manometer in conjunction with a barometer. The manometer will tell you the difference in pressure. That difference is then either added or subtracted to the barometric pressure. Any questions on that? So manometers were using YouTube way before YouTube was even invented. But I'm sure if you go on YouTube, there's probably a YouTube video of a YouTube and how to read it. All right, speaking of reading a manometer or a YouTube, group 2, what is the pressure in problem number 10? 794? Good. Why did you choose to add? Right, so you decided that there's more pressure than the atmosphere. Feel free to draw a picture. Lots of pushing over here, a little bit of pushing over here. I would write more. So how do you show 42 more? That's 42 more than 752. You're adding it. Show of hands, we got 794? Okay, sweet. Any questions? All right, and then I think we're up to group 3. How would you get number 11?
Would you just add
690 and 26. So you're saying this is pushing more? Yep, so it's more. Is the difference 26?
It is 20.
It's only 20. Yeah, so this is a little bit different. Rather than giving you the difference, they measured from down here. This is 26. This is 6. So the difference would be 20. So it's 20 more than 690. For a final answer of? 710. Same concept, it's just they gave you the numbers in a slightly different format. Show our hands, we got 710? Okay, good. Any questions I can answer? So again, your homework is page 23, 1 through 5. If you were a little shaky on that homework last night, maybe you also want to tie in maybe 6, 7, and 8. If you need just a little bit more manometer practice. Questions on that? All right, so now the two old essential questions should be able to be answered. For time's sake, though, we're going to move right into Boyle's Law. So let's go ahead and take a look at page 26. Based on where we're at in the schedule, needing to wrap up things next week, I can't give you a whole day to work on the POGL activity, but I'd say it's a pretty good activity that if you want to kind of see the history, these numbers right here are actually out of Robert Boyle's actual lab notebook from 1662. I found a cool website online. I think the Royal Institute of Sciences in England, they have like a digital copy of his lab notebook, pictures of it. So I got these numbers straight from his lab notebook way back in 1662. You basically go through the questions and it's going to help you come up with Boyle's Law. Basically what you find out in the questions is as pressure goes up, volume goes down. Okay, that's an inverse relationship. Mathematically, what do we mean by inverse? Mathematically, what is an inverse? It's a reciprocal, right? So we say that volume and pressure are inversely proportional. Or volume and inverse pressure, that's the reciprocal of pressure, are proportional to volume over inverse pressure. So volume and pressure are inversely related. So therefore volume and inverse pressure would be directly proportional, which means you can write a proportion. Normally we don't write reciprocals in the bottom of a fraction. Where would the reciprocal of a bottom of a fraction go? It's going to go to the top. So really we get V times P, first scenario, is equal to V2 times P2, second scenario. And that right there is Boyle's Law. I would have given you a whole class period to kind of mathematically work up to that point, but I can just give you that equation. It's on the back of the periodic table. Any questions on that? All right, so now let's use that equation. So we're going to do problems 15, 16, and 17 as examples, and then I'll give you 5 Boyle's Law problems just to make sure you're good to go. I like to draw little pictures to help me out. Kind of helps me wrap my head around the data. So, in problem number 15, one thing I did want to note, in your problem 15 right above it, does it say the average size of human lungs are 5 liters? Okay, I want you to change that to 2.5. I changed it for next year's packet. When I originally wrote this question, I did some research. I wanted like the real average human lung size, and I read that it was 2.5. Now I kind of read that as 2.5 per lung. It really should have been 1.25 per lung so that you have a total volume of 2.5. So I thought it was 2.5 and 2.5 giving you a total of 5. So let's just scrap the 5 and make it 2.5 total. That way it's actually a realistic problem. So when you take a deep breath, that's 2.5 liters. So if these people are at the top of the pool taking a deep breath, how big are their lungs? 2.5 liters. Again, not 5, 2.5. We changed that. Therefore, all the answers in the margin are going to be cut in half as well. What do we have sitting on our heads at the top of the pool? Air pressure. How much pressure? Approximately 1 atmosphere. Give or take a little bit, based on weather. Now we're going to dive down to the bottom of the pool. In this problem number 15, how deep is the pool? 12 feet? 12 feet. So now what do we have sitting on our heads at the bottom of the pool? We have 1 atmosphere of sky plus an additional 12 feet of water. Uh-oh. Can I just add those two numbers together and get 13? No. So if you look at the given information, what do they tell you about water and air pressure? Luke?
33.8 feet of water is equivalent to an additional atmosphere.
Right, so this atmosphere is enough pressure to basically equal out 33.8 feet of water. So rather than using 1 atmosphere, we'll use 33.8 feet. And over here, I'm not going to use 1 atmosphere, I'll use 33.8 feet of water, because then what can I do with 33.8 feet of water and 12 feet of water? Add them together. Would you agree you'll get 45.8 feet of water pressure? So at this point, we haven't even done Boyle's Law yet. We just got our 2 pressures equal to each other. or not equal to each other, but in the same unit, so we can use them and cancel them. From the previous page, what's the equation for Boyle's law? P1 times V1 equals P2 times V2. It is in a similar fashion written on the back of the periodic table. We'll talk about that next week. What's actually on the table is the combined gas law, but Boyle's law is a part of that. All right, I'm solving for V2. I really like to solve for that before I chuck any numbers in. Would you agree mathematically we're going to divide by P2 and divide by P2? So we get V2 is basically a proportion of the pressures scaling up or down the volume. It's basically the ratio of the pressures. Now, I always like to kind of logically think this through. We're going down in the water, therefore the pressure is going up. There's more pressure at the bottom of the pool. Because they're inversely related, what should happen to the volume? It should go down. I'm going to write that in my problem, because if I don't get a number less than 2.5, I know I accidentally flip-flop my pressures. So we have 33.8 feet of water pressure, 45.8 feet of water pressure. That's less than 1, so therefore we'll get a number less than 2.5. We need something about 3/4 of 2.5, probably close to 2. Chuck it in the calculator. 2 sig figs, what do you get? Luke?
1.8.
1.8. Can I get one more digit just in case we need it again?
1.84.
1.84. And what comes after the 4? 4. Okay, 1.84. I like it. Does it make sense? You feel that pressure pushing in on you at the bottom of the pool? Sometimes it kind of hurts. Okay, let's see what happens when we rise back to the surface. Question number 16. Let's just reset the problem. Okay, we're sitting at the bottom of the pool. How big are our lungs at the bottom of the pool? 1.8 with an extra little calculator for? How much pressure is at the bottom of the pool? A sky plus 12 feet of water gave us what? 45.8 feet of water pressure. When we come back to the surface, do we have any water sitting on our head? No, but 1 atmosphere would be equal to how much water pressure? 33.8 feet of water pressure, and we want to know how big will our lungs be. Any guesses before we do the math? We came back to the surface again. Hopefully they go back to normal, right? Normal size would be 2.5 liters. We don't want to pull a Honey, I Shrunk the Kids. You better fix my kids. You better be able to turn them back to the right size, right? So we've got P1 over P2, the ratio of the pressures, times V1 is equal to V2. So we have 45.8 divided by 33.8 feet. And we're going to multiply by the 1.84 liters. I'm hoping that's 2.5 liters. Cool. Nothing that magical about that. Hopefully we didn't change anything. What's cool, though, is that when we go to question 17, we throw on a self-contained underwater breathing apparatus. Better known as what? Scuba. Okay? You never want to scratch and sniff a sticker at the bottom of the pool, unless you have a scuba mask on, because if not, you know it's a trap. Okay, so don't do it. So, with a scuba mask on, you can take a deep breath at the bottom of the ocean, right? So, how big's the deep breath? 2.5 liters. We are, does it say 100 feet? We're 100 feet below the water. What else is on top of the water? 33.8 feet of atmospheric sky pressure. So a total pressure of 133.8? We want to know what happens if you rise to the surface of the ocean. What do we have sitting on our head at the top of the ocean? Just one sky? 33.8. How big will our lungs be? Well, let's take a guess. So pressure is going down, volume should do what? Should go up. Would you agree it's going from 130 down to 30? Maybe 120 down to 30. It's going down by a factor of about 4? So therefore, the volume should go up by a factor of about 4. So let's do it. We have 133.8 feet of water pressure divided by 33.8 feet of water pressure times 2.5 liters. Final answer, 2 sig figs. 9.9? Yay, we have super lungs. Bigger lungs the better, right? No, how big should our lungs be? 2.5 liters. What's going to happen if they're 10 liters? They're going to pop. Or you'll probably cry out in pain before you even get to that point. So one of the number 1 rules, anybody ever do any scuba diving in here? Okay, what's one of the number 1 rules to scuba diving? When you come up, you have to do what? Michael?
You have to go slow. You can't like rush up.
You do have to go slow. We'll talk about that in a second. But according to this, I can't have that much air in my lungs. I don't want to pop. You have to exhale. So now we have less air in our lungs so that when it expands, it goes to 2.5 liters. You got to exhale on the way up or else you're going to like pop your lungs or cause major damage to them. Why do we have to go up slowly? Well, because we have air in our bloodstream, right? You have oxygen in your blood. Now, the little bubbles are so small you can't see them, but would you agree those microscopic bubbles are also going to increase by 4 times? So if you go up too quickly, now those little microscopic bubbles become visible bubbles. What if they get stuck in your arteries? It's going to cause pain all over your body, causing a condition known as what? The bends, okay? That's bad. That's going to end your scuba diving career. If that little air bubble goes to your heart, it's going to cause a what? Heart attack, okay? Not a good thing. If that air bubble goes to your brain and your brain doesn't get oxygen, that's a stroke, okay? So there's lots of things you got to do to be safe in scuba diving. You always go with a buddy. You have a timer, a watch on, double checking, making sure you have enough oxygen left in your tank because you can't just rush up at the end. You got to go up slowly. You got to give yourself enough oxygen to go up slowly so that air bubbles don't form in your bloodstream and that you have to exhale on the way up. With that being said, any questions? All right, the 5 homework problems you're going to do here would be 1 through 5 on after the Boyle's Law Poggle page. It's what is my page 30. 1 through 5, page 30. Questions on that? So 1 through 5 pressure conversions, page 23. 1 through 5 Boyle's Law problems, page 30. I don't think that'll take you very long. Just some proportions, some fraction conversions.